Yo, what's up, everybody? This is Mr. Nixon. Just wanted to drop a quick line about the respiratory system and kind of discuss that in an organized manner. The respiratory system is probably one of those systems where it's chapter 23, and it's kind of it's interesting, but it's kind of difficult at the same time. And the reason why it can be kind of difficult is simply because there's these physics and biochemistry mixed in with this thing. And the chapter is, it goes into a lot of detail. And sometimes, if you're not careful, you get lost in that detail. So I kind of want to take some things and put it back together and put it in an organized fashion. I'll tell you right now, the secret to chapter 23 are pages 934 to 935. If you can walk through that entire process and understand the flow and how everything else in the chapter falls into each one of those 8 boxes, then you are set for this chapter. You can walk away from this chapter and be good. So I kind of want to walk you through those 8 boxes a little bit. Excuse me. It's the weekend and I've gotten no rest, and I probably look like it. and almost kind of feel like it. So I'm actually getting a good break sitting here talking to you guys. So if you don't have your textbook and something to take notes with, might want to pause this video, stop, and go get your textbook and get a notebook or something to write notes with, because you're going to need that. You're going to want to jot some notes down, so some things that I'm going to say. And you want to follow along in your textbook on page 934 and 935. This is out of the second edition. So go ahead and go do that now. Okay. So you should have paused. Now you've unpaused, and now you're back with me. Excuse me if I get a little bit of water. Voice hasn't gotten a chance to heal itself since last week. But anyway, that's besides the point. Let's talk about the respiratory system. So something you need to remember about the respiratory system is the reason why you have it is so that you can get uh, air is you want to get air from the atmosphere, or let's be specific, you want to get oxygen from the atmosphere around you ultimately to your body cells. So you're going to do that through stages. You can't separate the gases of oxygen and carbon dioxide and nitrogen and water vapor and all that stuff. You can't separate those individual gases out of the atmosphere before the air enters your lungs. So your first goal is to simply get atmospheric air out of the atmosphere and into your alveoli. Now, if you haven't studied the respiratory system anatomy, you need to go back and look at that. And I also have some videos that deal with that. So if you want to hit those videos, that's cool. If you don't know where those are, just let me know, because you can go to the Professor 77 on YouTube and you can check those out. But your first goal is to get atmospheric air from the atmosphere to um, to your alveoli. And the reason specifically for your alveoli is because that's where your gas exchange is going to take place. That's where you're going to be able to exchange the oxygen from your atmosphere um, with the carbon dioxide that just arrived at your alveoli via the bloodstream. So our first step, step number one, getting atmospheric air from the atmosphere into my alveoli. Then the next step is to get oxygen, not air. Oxygen is a part of air. The next step is to get oxygen out of the air in your alveoli and into your pulmonary capillaries. Then, after we get oxygen out of the alveoli and into the pulmonary capillaries, the next step is to bind that oxygen to the hemoglobin in your red blood cells. Now, that's very important because even though the solubility of oxygen in water is it ain't all that great. It's kind of low. So we want to do our best to bind oxygen to something to carry it in the blood. Otherwise, it's just going to leave your bloodstream. So we bind oxygen to hemoglobin within red blood cells. 98% of all the oxygen in your blood is bound to hemoglobin. That keeps it from disappearing on you. So then the blood flows through the body. You therefore carry that oxygen to the capillaries, the systemic capillaries of your body. Now, when we say systemic capillaries, we're talking about the capillaries that go to the tissues of your body, your brain, um, your feet, your kidneys, your liver, the muscles, your spleen, everywhere, all of this stuff. So we get that oxygen to the pulmonary capillaries, and then through a pressure gradient, this oxygen is going to detach from the hemoglobin of your red blood cells at the systemic capillaries, and it's going to diffuse from the capillaries into the surrounding tissues because of the pressure gradient. Because when you have a gradient, things go from a high position to a low position. Just think of it like a hill and riding a bike. I mean, if you were at the bottom of a hill on a bike, your bike wouldn't naturally roll uphill. That's crazy. That's some Three Stooges stuff right there. So, but you would, if you were sitting on a bike on top of a hill, then you would roll down that hill because things go from a high position to a low position. That's just the way that law works. So oxygen diffuses out of the systemic capillaries and then into the surrounding tissues. Well, those tissues, the cells in those tissues, they use that oxygen, and then after they use that oxygen, they create carbon dioxide, which is a waste product. The carbon dioxide then follows the same rule. It diffuses from a high concentration to a place of low concentration. So there's a lower concentration of carbon dioxide in the blood that just showed up at the capillaries. Then there is carbon dioxide in the tissues. Why? Because the tissues just use oxygen. The tissues are alive. They're generating carbon dioxide constantly. So they have a much higher concentration of carbon dioxide than the incoming blood that's chock full of oxygen. Therefore, the carbon dioxide naturally, because of the pressure gradient, the carbon dioxide diffuses from the tissues and into the systemic capillaries. And once it does that, it can actually travel back to the lungs via the blood by a multitude of different ways. One of the ways that it travels is the 7% of carbon dioxide actually just dissolves into the blood plasma, because carbon dioxide is actually more soluble in water than oxygen is. That's why we use carbon dioxide to make soda, because carbon dioxide dissolves in the water so well. So 7% of carbon dioxide dissolves in water. Then another 23% of carbon dioxide actually binds the hemoglobin. So it replaces water. Replaces oxygen. I'm sitting there drinking water. And then 70% of the carbon dioxide is actually undergoes an enzymatic transformation within the red blood cells, and we ultimately convert it to bicarbonate ions. And so 70% of that carbon dioxide goes into the red blood cell. It's exposed to enzymes, which converts it ultimately to bicarbonate ions. We dump those bicarbonate ions into the blood, and it travels all the way to the lungs, where it goes to the pulmonary capillaries, and all of that carbon dioxide, including the bicarbonate ions, which then re-enter the red blood cells, undergo an enzymatic transformation and then changes back into carbon dioxide. And all that carbon dioxide therefore diffuses out of the blood into the alveoli, because at that point there's so much carbon dioxide in the blood, the pressure gradient moves carbon dioxide into the alveoli, because now the amount of partial pressure in the blood, once it arrives at the pulmonary capillaries, is higher than the pressure of carbon dioxide in the alveoli, which automatically pushes it right out of the blood and into the alveoli, and then you exhale and you release that carbon dioxide. So that's a walkthrough of page 934 and 935. I'm going to do another talk here in just a moment where I want to kind of discuss where do the gas laws come into play with these blocks. That's great, Mr. Nixon. You talked about these 8 boxes, but these doggone gas laws, how do they apply? Tune in soon.